Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Welcome back to part 2 of Gravitational Lensing on Whimsical Wavelengths. In part 2, we finally get to the real star of the show, strong gravitational lensing, and the paper that was the underlying topic that brought this all together. Euclid, a complete Einstein ring in NGC 6505. Okay, a lot less setup this time. No need to stretch this out like gravity stretches time. That said, it's probably a good idea to set up redshift and blue shift. It's definitely going to come up. Standing by a road, you can instinctively hear whether a vehicle is coming towards you or moving away. Why? Well, because of the Doppler effect. In this instance, the movement of vehicles change the frequency of sound waves. Coming towards it compresses the wave, making them sound higher pitch, and moving away is the opposite. You can pretty much hear exactly what I'm talking about on a race car. How did gravity stop the reckless driver? Well, it pulled some strings, mainly the ones holding the car to the road, before everything gets pulled downhill. The same thing with the Doppler effect happens with electromagnetic waves. Most objects in the universe are moving away from us. That stretches out the wavelength, shifting the frequency to lower values, which we call redshift, because if you're in the visible spectrum of light, red is near the lower end or has a lower frequency, longer wavelength than the rest of the visible spectrum. And we use the term blue shift for objects moving towards us, as blue is towards the higher end of the visible spectrum. All right, time to jump in. Whimsical Wavelengths is back. Yes, this is part 2. I didn't record it back to back and then have to split it. I really did plan this one. So welcome back, Dr. Georgios Vernardos, and we'll continue our discussion and get to the real star of the show, which is strong gravitational lensing. Yay!
Hi, Jeff. Thanks for inviting me back. I'm happy to be here again.
Awesome, and gladly willing to impart your knowledge on this topic that I know so little about, because I mean, it's images, arcs, and rings, oh my, strong gravitational lensing. I guess this is an example that's much closer to the lens of my glasses, as it creates almost a complete image from what's behind it. And I use the word plural here, images, for a reason. How and or why is that?
Remember when we discussed the deflection angles due to curved space-time? Then when you have weak lensing, for example, which we briefly talked about last time, you have these deflection angles that are the deflection itself, so the angle is small. So you have slight distortions, very slight. Strong lensing, as the name suggests, you have stronger deflections, which means this is usually because you have a closer alignment between your lens and the source. And stronger deflections mean that you can have rays being deflected from both sides of the lens, not just one. That would be weak lensing. And that would be when there is less of an alignment. So when there is more alignment, you have stronger deflections. Therefore, rays from both sides of the lens or all around the lens can be deflected and focused back to the observer, and that's why you get multiple images. That's why there is a connection between strong, the word strong in front of lensing, and the word multiple in front of images.
Okay, so we can get multiple images of the same galaxy or source behind the lens. Does having multiple images or looks help us determine anything about the source behind it?
It kind of does. It also helps us learn about the lens in front of it. So when you have multiple images, when you have strong lensing, strong deflection angles also mean higher magnification. So this is the first thing to keep in mind. So you have a better telescope, let's say, that is there, a stronger, more powerful telescope that helps you resolve the background source. Then it's also important that the background source, so the lensed features of the background source, the multiple images and the arcs, they cover a bigger area on the sky, simply because you have a larger surface, they are being lensed into a bigger another image with a bigger surface. This helps, for example, to probe different parts of the lens because you have a bigger surface on the background. Think of it as a bigger lamp behind something that is dark, right? And you want to figure out what this dark thing really is. So if you have a bigger lamp, you can illuminate a bigger part of it. So this helps us, for example, to try and identify dark matter substructures, dark matter subhalos, smaller halos of dark matter, whereas that is our what we are hunting for. It will be these sort of observations will be very powerful to discriminate between different dark matter models.
I think you just used a term there I don't think we've covered yet in the first part, and I know
Okay.
it'll come up in a very near episode, hopefully.
Yeah.
Dark matter halo. What does that really mean?
Right. So this is halo is a term that we use throughout cosmology. Whoever works on galaxies, simulating them, observing them, and not just galaxies, but also cluster of galaxies and so on. It's a very basic term. It's a loose term. It basically means a conglomerate of mass that happens from the biggest sizes at the biggest scales, galaxy clusters, for example, to the smallest ones, to our own galaxy, for example, or to smaller galaxies, dwarf galaxies, like the Magellanic Clouds, visible from the southern hemisphere. These are dwarf satellites of our own Milky Way. So halo, think of it just as a sphere within which gravity dominates. So things are getting condensed within this sphere. Gravity dominates as opposed to the cosmological expansion, the Hubble expansion of the universe. So you have two competing forces there, gravity versus the expansion of the universe. Within these halos, gravity has dominated because there was enough matter that was close enough to cause what we call hierarchical formation of structures through gravitational instability. It's a bit of a railroad sentence, this one, but it means basically that gravity dominates and matter starts to collapse to form nebulae, and from the nebulae you form galaxies, and within these galaxies you start forming stars and so on. So the term halo is, think of it as, this sphere that is usually a galaxy lives in it, but you can also have bigger halos where many galaxies reside, or smaller halos where you can have dwarf galaxies, or even similar smaller halos which do not form stars. So this is where there is a lot of interest. Why? Because these halos contain matter, and 80% of that matter is dark matter. So whatever 20% is left has to be able to form stars. And if that happens, then you see it, either as a dwarf galaxy or as a cluster of galaxies. But in some cases, these halos can be completely dark. So they were not able to form stars. The field of star formation is a very rich field in astrophysics, and we still need to understand many things around it. But the simple thing to keep in mind for now is that some halos may not be big enough to form stars, to contain enough baryons, enough normal matter to form stars. So they remain small and dark forever.
So what you seem to be suggesting that there are, for the lack of a better term, dark galaxies out there where there might be a lens, but there's no visible matter associated with it.
Exactly, almost that. So at the scale of the mass of a galaxy, these halos should contain enough baryons to always form stars. So we don't worry about such dark halos. But at smaller scales, for example, satellites of the Milky Way, the Magellanic Cloud scale, it's possible to have such dark halos or even smaller halos. And how many such dark halos you have is very sensitive to the type of dark matter that exists in the universe. So I'm not sure we mentioned this last time, but correct me if I'm wrong. The cold dark matter paradigm, which explains the universe on the biggest scales, these scales are anything that is larger than a galaxy, is very successful. So it can explain almost everything, almost all of the observations that we have. But in smaller scales within a galaxy now, and dwarf galaxies and so on, this cold dark matter paradigm is starting to have some problems, cannot explain all the observations, and there we need to invoke other types of dark matter, warm dark matter, self-interacting dark matter, and all of this has basically to do with the properties of the putative dark matter particle, right? And you see now where this is going, because some halos can be dark, or sub-halos, the smaller ones, smaller than a galaxy. We don't see them, but they still deflect rays. So they can still act as a small gravitational lens. So you have the big gravitational lens with its dark sub-halo satellites around it, and if you have a lens source, you have a big lamp behind these dark sub-halos, so you could potentially see them and detect them. And now we close this little loop about halos and dark matter.
Sweet. This is a yes or no question. Have we detected any?
We are working on it. We have detected some, and through a technique called gravitational imaging. And I have been working with this technique. I have developed analysis tools for this and so on. So we have detected halos that they appear dark. They are not really dark. It's just that they are so far away that we don't see the light from their stars, because from the mass that we detect, they should have stars as well, but we need much more powerful telescopes to see them. For example, we're putting in proposals to use the James Webb Telescope to detect the light from these dark subhalos that we have detected through their gravitational effects in a gravitational lens. And also another thing to note is that the bigger these halos, the more easier they are to detect, or the bigger these subhalos, I should say. They are still they are always satellites of a bigger lensing galaxy. So the bigger they are, the easier they are to detect, but they're also consistent. These bigger subhalos, they're consistent with more flavors of dark matter. In order to be able to tell apart these different flavors of dark matter, you have to detect smaller mass subhalos, and this is harder. So there are 3-4 detections so far from gravitational imaging, this business with gravitational lenses, of subhalos, and we really aim for more in the future. And I know I've just been at a conference, and I know there is a group of colleagues who are working on modeling gravitational lenses in the radio, and they have detected a very small mass subhalo. The paper should be out soon. What is the difference in the radio? In the radio, you have much higher resolution than in the optical. You can achieve that. You can have, in the optical, you can have a resolution of a few tenths of an arc second, but in the radio, you can have milli-arc second resolution, so almost 100 times, 1,000 times better.
And we already had a discussion about resolution, that resolution is really important in this process.
Exactly, and especially for smaller mass subhalos, which are the ones that we need to tell different dark matter models apart. Of course, it's always hard to model these things and get nice, robust results out of this. So it's a very active field. There is a lot of people working on this, but yeah, it's very challenging to perform these measurements.
Well, when you do, because it sounds like you're working on it, let me know, and I'd love to come back on and discuss it. But for now, we should probably pivot to the arcs and Einstein rings, which are both strong gravitational lensing phenomenon, in the sense that they're the same, they work from the same process, if I've understood everything so far. But what's really the difference between them?
Right. So that's a pretty simple to visualize, to think of. It's just the alignment. The phenomenology of a strong lens, of a strong galaxy lens, it's pretty simple. You can have 2 or 4 images, or a full complete Einstein ring. Let's start from the complete Einstein ring. This is the easiest to visualize. It's when you have perfect alignment and you have a nice, let's say, well-behaved lens. What do I mean by that? You don't have some galaxy that has been through a merger, for example, and its mass distribution is a bit fragmented, is a bit like a train wreck, is a bit all over the place. You have a nice, relaxed galaxy, dynamically speaking, that its mass distribution is, think of it as a sphere, right? Something like that. Then, when it's perfectly aligned with the source, you get a ring. The source is lensed into a ring. As you start moving the source away from the straight line that connects the observer, the lens, and the source. If you start moving it a bit further, so a bit misaligned, you start fragmenting this Einstein ring usually into 4 arcs, and they can have a configuration of a cross, or they can have a configuration of 3 of them on one side and 1 of them on the other side of the lens. And if you further misalign, so you move further away from the lens, you move the source further away, the 4 arcs will merge into 2. So the 3 of them will merge into 1, and the other one will also remain where it was. So you, instead of 4, you now have 2. And it's pretty simple. And if you keep moving further away, then one of these 2 arcs will get very, very dim and non-detectable anymore. And now you enter the regime of weak lensing. You have an arc which is not multiply imaged, and it's not, how to put it, a high fidelity copy of the source. It's a distorted copy of the source. It's still an arc.
Well, now between that and your first description there, I think that covered it perfectly. I think I fully understand the difference between them now. Hopefully you listeners do as well. Okay, well, we've already kind of touched on it with that this discovery came from Euclid because it was able to see a wide field of the sky while at the same time having high resolution. But what is the ring at the center of this paper, and how was it discovered before we move in and talk about some of the data?
Mm-hmm. So this is a very nice story behind. There is a very nice story behind the discovery of this ring. First of all, this lens is actually an NGC galaxy. What does that mean? NGC stands for New General Catalog, and it was one of the first catalogs of galaxies compiled in astronomy. So there were some astronomers in the 19th century. They had some access to telescopes, very primitive telescopes compared to what we have today. So they could see these nebulae in our own galaxy or nebulae outside our own galaxy, which were other galaxies, but it took some time to realize that, obviously. And one of the objects that they have took note of, because it was bright enough, it's this NGC Galaxy 6505. This is how the number they assigned to it in their catalog. So this is a nearby, relative close to us galaxy, and it's because it's close to us, it's bright enough for people in the 19th century to observe it. It was bright enough, but they didn't have such good instruments to be able to see that it's a lens, both in terms of resolution and some other properties. I will get to this point in a minute. So because this object has been known for decades, and among with other objects has been cataloged and its properties observed throughout the years, things like its brightness, it remained constant, which is something that is useful for astronomers to orient themselves and calibrate their instruments. This specific field of view containing this galaxy was chosen to be part of the Euclid calibration fields. What does this mean? It means that the Euclid Space Telescope was re-observing this area of the sky every now and then, much more frequently than other parts of the sky where it would go and survey as well, to calibrate its instruments, to say, look, this is the brightness I detect for this object, this is what we have in our catalogs, am I good? Do I need to change the setup of my instruments or something like that? So it kept doing this. So there was a lot of data coming early on from this field of view on the sky. And one of the colleagues was looking through this data. I think he was doing it just out of curiosity. And he got the image on his computer. He was changing the contrast and so on. And he realized that in the center of that galaxy, buried in the brightest parts in the center of that galaxy, there was 4 lensed arcs that formed an almost complete Einstein ring. And he was the first one to ever see this. So this object has been seen by astronomers in the 19th century. In fact, it's recorded in 1885.
Wow.
And the story is that there was an amateur astronomer who cataloged this object from his barn, from his farm. And they didn't have good enough instruments to see the lens, which is very ironic, if you want, because this happened in 1885. So we had the data for this system, of course, without the resolution, without what we know, without what Euclid unveiled. So we had that then. And then in the beginning of the 20th century, Einstein came with his theory of relativity about bending light bending through curved space-time and all this stuff. And it's recorded that Einstein thought that gravitational lensing is a prediction of his theory. And in fact, if you remember from our previous conversation, it was during the Eddington expedition with the solar eclipse, it was used to confirm the predictions of the theory of relativity. But Einstein thought that gravitational lensing of galaxies, for example, would never be observed. It would be a too weak an effect. We would need extremely sensitive instruments to detect it. So he thought, and it's on record, that this would never be observed. While at the same time, there was a lens, this NGC 6505, that was known and cataloged. It just, we're not able to see that it was a lens a couple of decades before Einstein even thought of this. So
Wow.
There's a bit of irony here in history.
Just out of curiosity, if you can remember, when they first found this galaxy, did they label it as a star? Did they label it as a nebula? I mean, they thought it was within the Milky Way. I mean, we've covered that to some extent because Hubble was the one that first noticed that we're seeing outside of our own galaxy. But do you know what it was categorized to begin with?
Nebula, mostly
Okay.
nebula. So all of this stuff, so these NGC objects, some of them are other galaxies, some of them are nebulae within our own galaxy. So
But
they
this
were
one-
all just cataloged as bright objects in the sky visible from the telescopes of the time.
Awesome. That's cool. I love the deep dive into history
Yeah.
every once in a while. It's good to know where we've been, to know where we're going. Okay, so now that we've talked about Euclid again, and we've set the stage, there's more than just Euclid in the paper we're discussing. There's other data
Right.
from other things like Keck, Cosmic Web Imager, and the Dark Energy Spectroscopic Instrument. What is it, this other
Right.
data and observations?
So the first thing to note is that Euclid was able to do this discovery because not only had a very high resolution space-based telescope and a large field of view, and it happened to observe this field of view, it also had a tremendous signal to noise ratio. What does that mean? It means that when you are looking at something that is dim or something that is buried within the light of another very bright object, in this case, this is the case we are talking about, the lensed features are buried in the center in the central region of that NGC galaxy, which is bright on its own. So when you're looking for tiny variations in this flux of light, you need a very good signal to noise. Basically, you need a long exposure, as photographers do from the Earth and with other things, not necessarily astronomical photos. So Euclid had this as well. It's a tick on its on this checkbox. It also checked this box, and that's why we're able to see it. Hubble would also have been able to see it, but it would need longer exposures. So and longer exposure is obviously more expensive. It needs more telescope time. So this combination of resolution and signal to noise, high signal to noise, long exposure was what led to this discovery, what made it possible. But the instrument on Euclid, it's a very specific one. It's called the VIS instrument, coming from visual, because it's a band that detects, it's just a filter. Think of it as a filter on top of your camera that allows photons within the visual spectrum to go through and it covers almost the entire visual spectrum. So from blue to red without any discrimination. So it collects all of these photons indiscriminately. Euclid also has some infrared instruments, but they have lower resolution and they are used for other things. So you just get one image, high resolution image from the telescope, from Euclid, that has all of these photons stacked, photons of different colors stacked in each pixel. And it helps us identify the features of this lens, but we need more in order to make sense of it. And redshift is one of these one piece of additional information that we need in this case. What is redshift? Redshift is basically an indicator of distance, how far things are from you. And we obviously knew how far this NGC galaxy was, but we're talking about the lens galaxy here. The source, we had no idea when we got the Euclid image, and there is no way to find out the distance of the source through its redshift from Euclid data. So you need additional data. And spectrographs are the ideal instrument in order to be able to obtain a redshift. So what is a spectrograph? It's basically an instrument that measures photons of all different colors, even beyond the visual spectrum, individually. So it has its bins, let's say, where it gathers its buckets, where it gathers photons from a specific pixel, but it sorts these photons according to their color into these different bins. And you get a spectrum of what you're observing in this way. And in this spectrum, you can, from this spectrum, you can infer the redshift, you can measure the redshift and infer the distance.
Wait,
so we need
how? Like, doesn't it matter on the source?
So how does this work? So when we have, let's take, for example, some element, let's take hydrogen, okay? And you have this, and by the way, the universe contains a lot of hydrogen. It's one of the dominant elements. When you heat hydrogen up on Earth, it emits in specific wavelengths. It has to do with quantum mechanics. It will not, for example, if you heat it up, if you put it in an electric tube, for example, and you excite hydrogen, you give it energy, it will re-emit this energy or radiate it away by cooling off, for example, but it will do this in specific wavelengths, in very specific colors. And I remember we did this experiment in the lab when I was a physics student, and you could see 4 lines of hydrogen, one in blue, one in orange, one in cyan, if I remember correctly, and one in red. These lines are at fixed wavelengths anywhere you are in the universe. But if you happen to accelerate, or if you have a velocity away or towards the observer, so let's say that you have a bunch of hydrogen moving away or towards you, you get the Doppler effect. What is this Doppler effect? The simplest way to explain this is the siren of an ambulance. If the ambulance is parked right next to you and has the siren on, you hear the true frequency, the true wavelength. So you see the true color. If the ambulance is rushing towards you, you hear a higher pitch. So you hear a higher frequency. And if it's driving away from you, you hear a lower frequency. This is an experiment that everybody can go outside and do, especially here in New York, where I live.
Yeah, I just to interrupt a second here. Maybe it's something that I don't understand, because I hopefully did a good job of explaining this with a slightly different analogy using race cars in the opening. I even made some car noises, which you will hear when I'll send it to you. It's going to be terrible. What I mean is, what I mean is, by how do you tell is, like, let's say you're getting a radiation source, maybe it's a quasar behind it or something like that. You're not necessarily going to get a lot of hydrogen in that signal, would you?
Right. You may or may not get hydrogen, but it's not just hydrogen, it's other elements as well in the universe.
But do you have to make an assumption of the source? Like, you then model and say, okay, this is what we get. This is the most likely source. Now we know about that source. Now how much did we shift that source to get what we got?
Exactly. So when you observe a galaxy anywhere in the universe, it's because the universe is expanding, all galaxies are moving away from you, so their frequencies, the frequency of light coming from them is lower, which means redder, hence the term redshift. So when you see that, when you see spectra of galaxies, it's relatively a straightforward job to fit this spectra with known emission lines from a bunch of elements and figure out, if you see some line in some wavelength, you can say, oh, this is most likely the line from this element. And therefore, you see the difference in the wavelength or in frequency. And therefore, you say, oh, this is by how much, this is the speed with which is moving away from me. Therefore, I can estimate its distance, and I know how far it is. This is relatively straightforward, and this is exactly what we did in this paper when we went to get spectra of the source in this lens, got that, modeled the spectra, found the redshift, because again, now we know how far this source is. Now we can put better constraints in our lens models and understand the system in a better way.
Makes a lot of sense. Okay. Now
we made a big deviation here talking about the...
No, this is right. This is right on track, actually, because my next question is, what is the source? Like, that's literally the next question I wrote for this.
Okay.
So what is it? I mean, we just went and explained it.
The source seems to be just a normal galaxy, a
Oh,
normie.
that's
Nothing super exciting.
it's almost
Uh,
anticlimactic. But
yeah, I'm sorry for that.
so how far away is it? Or is that also normal? Is it not like close to 10 billion years? Is it just right
Uh,
behind it?
no, it's much less than that. So the redshift that we measured for this object, it's 0.4. But again, this really means by how much the wavelength of these emission lines of specific elements is shifted. It's redshifted. So we need to convert this redshift into distance. And to do that, it's not that straightforward. So it's slightly complicated. You need to know how the universe is expanding and has expanded through its lifetime, which depends on things that are still unknown, like dark energy and dark matter. So it's not super complicated, but there is a little tiny question mark. But in any case, we can do this relatively confidently. And the redshift of some people know this, they can do this conversion by heart. I'm not one of these people. I know, for example, that as a rule of thumb, a redshift of 1 corresponds to a distance of around 6 billion light years, which is roughly half the age of the universe. So redshift of 1 is roughly half the age of the universe. A redshift of 0.5 would be, naively thinking, would be around 3 billion years, something like that. It's not a linear relation, which complicates things. But anyway, so yeah, it's relatively a young galaxy, not so far away. We're not looking too far away in the past. 3 billion years is still manageable. It's still the universe as is around us today, more or less. To give a bit more context here, the most distant galaxies that we have seen are quasars, because they're very bright, therefore we can see them from far away, around redshift of 7, 8, something like that, which is 12 billion years ago, something like that.
Wow.
So very young, in the very early
Parts of the
life
universe.
of the
Yeah.
universe.
Wasn't there? Oh, no, sorry. This is going to be a complete deviation and not in any of the questions you might have expected from me. But wasn't there also something recent in the news, quote unquote, in cosmology, that there's some hints now that the expansion of the universe has not been constant, that there might be a bit more to it?
Yes. This is again another deviation, but yes. So the expansion of the universe was discovered by Hubble 100 years ago or so. He came up with a factor to describe this expansion, which is constant. It's the Hubble constant. This factor relates distances to recession velocities, to how far things, how fast are moving away from us, so how fast the universe is expanding. And it was a constant, which means a constant rate of expansion of the universe, constant velocity with which everything flies away from everything else in the universe. The quality of data that Hubble had back in the time allowed him to do this good enough. He was the first one to do this. But obviously, since through the decades, the quality of data available to us has improved. And in the late 1990s, there was this discovery of the accelerating expansion of the universe. So this expansion is not constant anymore, it is accelerating. That led to the postulation of dark energy. Dark energy is the reason that this acceleration happens. When you have acceleration, you need to give it energy to accelerate anything in the universe, on Earth, everywhere. Remember, Newton's law says that things like to move with constant velocity, but if you want to change their velocity, you have to give energy to them or act on them with force, it's the same thing, or remove energy from them. So dark energy was invented to explain the accelerating expansion of the universe. And since then, there have been efforts to really understand this acceleration, this accelerating expansion. And with this new data now, there is evidence that this acceleration has not been constant itself either, adding more to the story. So we started from constant velocity, then we moved to constant acceleration. Now we move to, we have evidence for non-constant acceleration throughout the age of the universe. Of course, this needs to be confirmed with other observations. It will take time. It will take maybe even decades to really pin down what is really happening, because the simplest model, let's say, to explain this non-constant acceleration is a linear model, like a straight line. But you can also have more things there, and these are just phenomenological models. Then we need to link this to what is actually dark energy, what is it made of, why it's, if it's a linear time dependence of the acceleration, why not, why it should be, why it shouldn't, and all this stuff. So there is a lot of meat in this.
I guess I don't feel bad asking this question, because the next part is to step into the modeling that's in this paper, and to some extent distances, how quickly they're moving, what's the distance to the thing behind it, which is based on its redshift, and its distance is all kind of intertwined, even if it's at the 0.00001% of the answer. So my limited understanding of reading the paper is that the modeling that's done on these lenses seems to be somewhat similar to what I do in my own field in geophysics, in the sense that I'm looking at Earth properties. And there's a lot of talk about the different variables and degrees of freedom in both types of modeling here. In my case, I'm producing a model that is non-unique. I'm producing something that doesn't have a unique solution, because there's more variables or more unknowns than there are knowns. So is this similar to geophysics? That there's more unknowns, so we're getting something that is not a unique solution for the system?
That's a very good question. And it's an active debate among myself and my colleagues, how we do these models, how trustworthy these models are, and whether we can constrain, we have our results are really robust, or it's just some solution that happens to make sense and we adopt it and we move ahead, but it's not the full story. It's a very nice question. The answer is that it's almost the same problem. It's an inverse problem. You have an image, you have the data, and you're trying to reconstruct nature, something that is there. In the case of lensing, what is there is the true source, the light distribution of the true source. So we are trying to de-lens the source that we observe. So we have no way of having the true image of the source. We must reconstruct it. Reconstruct is the key word here. And at the same time, we also need to reconstruct the thing that is causing the lensing, the mass of the lens.
And I guess dark matter makes it hard because you can't see some of that, right?
Exactly. And this has three parameters. These are three parameters in your models. What is the mass of the lens? What is the dark mass of the lens? Is it spherical? Is it elliptical? Does it have these multiples, which is something that is also in the paper? Basically, for many years, the easiest, or what could explain the data sufficiently, was spherical cows in the void, right? It's this kind of anecdote. So we model all galaxies as ellipses, and it turned out that we could reconstruct the lenses good enough for what we needed them for in the last 20 years or so. In the last 5 years, though, the debate has shifted and said the quality of the data that we are getting and will be getting soon with Euclid, JWST, and all these things will be good enough to go deeper into more detailed models. We know that galaxies are not ellipses, right? We know that there is more to the story. So let's try and see now whether we can incorporate this in our models and so on. It's very similar to geophysics when you have seismic data, earthquake data, and you try to reconstruct the Earth's mantle and all this kind of stuff, or find where oil is and minerals and this kind of stuff. It's also very similar to medical imaging. You go inside a tomographer, and you have all these detectors, the magnets spinning around you. The data that this machine gets needs to be de-lensed in a way to reconstruct your tissue, the bones, your brain, all these kind of things, right? It's a very similar problem. You also talked about the number of parameters. In our case, we still have less free parameters than data. So our problem is over-constrained. So we have more data than free parameters. So we are, it also depends on who you ask. Some other models are super free, so they have many more free parameters. So they are under-constrained, less data than parameters. So
okay,
we have this problem. Yeah.
But But so if you have more data than parameters, does that mean that some of the data sets are fighting each other, so to speak? Like they actually show something slightly different, and then the model has to come up with like something in between them?
So we have more data than parameters, but we cannot solve the problem directly. This is our problem. It's basically it boils down to a matrix inversion,
Okay.
which we cannot perform because it's an ill-posed problem. This is the term.
Okay,
in
so there we go.
mathematics.
Yes. That's where I was
Now we
going. I'm
speak
like,
the same language.
that was it. And you were trying to, in my mind, you were suggesting that it wasn't an ill-prose problem because you had a lot of data, but it is.
No.
So
Yes.
it still has more unknowns than direct knowns. And so you're having to mathematically create models iteratively to reproduce
Exactly.
the data that we have. And the more data we have from different sources, the more likely we're going to get to the correct answer.
Yes and no. In order to solve this ill-posed problem, we need to assume priors. And now we're speaking again the same language here.
Yes, we are. So, in my case, it's geological priors. So where is there a fault? What's the density of a particular layer, etc. In this case, we're talking what kind of priors?
How does a galaxy look? This is our prior. So when we see the lensed galaxy, right, we don't know how the true image of this thing looks. So our prior is that it should be a galaxy, basically. And there is a bunch of parameters that describe how galaxies look. And we assume this as priors. And that helps us invert this matrix and solve this ill-posed problem. Now it's not ill-posed anymore. We have these priors come to help us. But, in Bayesian statistics, and not only, the debate now becomes data-driven or prior-driven solution, right? So we have to strike a good balance there and understand that regardless of which one it is, our priors are not biasing us in some way, and so on. When it comes to the total mass of the lens to first approximation, or the light of the galaxy source to first approximation, we're doing well. These uncertainties, these biases that creep in, do not affect by too much what we understand of this. But if we want to zoom into substructures, to subhalos, to these dark halos that are smoking gun for different dark matter models, then these biases are major. They can cause you to detect, for example, a small mass subhalo, which is not there, it's spurious. It's just because your method is biased in some way that it pops out as a possible explanation. We really need to avoid this. And we're working hard, me and my colleagues, to understand this and make sure that our results don't suffer from such biases. It's a very ongoing thing, and it's also why lensing is a hard business, and why geology is also a hard business when you have such kind of inverse problems.
For sure, and maybe I want to poke at that a little bit, but just one more time. So in my case, sometimes when we put in something like in my field, we always do at least 2 inversions. We solve one without any priors to make sure the data is doing what it needs to do. It's giving us something. And then if the client or the company has given us something to put in there, we'll put it in there. But usually we can tell pretty clearly whether or not something is reasonable based on how well the inversion can fit the data. So how well does the resulting model reproduce the observations? So I assume to some extent that game is going on in this field as well, right? They're testing different models by changing the priors to see what kind of, we also use the word artifact. So if it starts to produce something, like you said, which is weird and doesn't make any sense, we call that an artifact. And that's usually key to going, okay, I did something wrong here. So I assume that there's this game going on as well within gravitational lensing.
So I'm very happy that the discussion came to this, because I kind of anticipated that we would find some common ground in the methodology when you told me that you are a geophysicist. So you know, and I knew about the common framework that we use to solve both problems in both fields. So I'm very happy we came to this common ground. The answer to your question is yes. We also try to check for artifacts, try to penalize, things that are unphysical and so on. It's the same game. It's almost, if we sit down and write the equations, I'm sure it will be almost the same equations.
Yeah, especially the optimization side of things, I would imagine.
Right, right. So we follow this Bayesian approach, comparing models, whichever model has the higher evidence. So Occam's razor as well, whichever model has the fewer parameters, but it still fits the data in a very good way. We chose that one. It's the same business. As soon as you enter the analysis part, it doesn't matter whether it is lenses or something else what you're looking at. It's exactly the same methodology. We are now in hardcore inverse problem, math, statistics, all this stuff.
Yeah, for sure. Okay. Now, I guess the right way to describe this paper is that it's the first attempt at modeling this system. There will probably be other, I would imagine, to come. But in this modeling, what did you find, or to rephrase, is there any interesting implications from it?
Right. So, and this is a very good question, actually. It will clarify a few things. So to first approximation, the model that we have in this paper is good enough so we can learn things about, in combination with other data, so from the spectrographs and so on, we can study the baryon versus dark matter or baryonic matter, what we see in stars, versus the total matter that produces the lensing phenomenon in the lens. So we can do that, and it's very interesting to do that. Why? Because what happens, the balance between baryons and dark matter inside the cores of galaxies is important, and it affects galaxy evolution. This is galaxy evolution, how galaxies are born and how they evolve, and what is the interplay between dark matter and baryons. In other words, how baryons collapse to form stars, how if you have more dark matter or if you have less, how are these things distributed in the centers of galaxies, in the outskirts of galaxies. These are still very active fields of research. So again, lensing is unique because it probes the total matter, not just what you see shining. And in this specific galaxy, we are able to do this and learn, for example, the balance between dark and baryonic matter in the center of that galaxy. This is useful to know for outside lensing, right? For all people studying galaxies. So this is good enough. We can also learn things about the size of the source, how big it is, star formation in the source. So now we're using the lens as a telescope. We forget about the lens galaxy. We use it as a telescope, and we can say, for example, this much star formation is happening at however many billion years away this source is. In this specific case, it's not really spatial, but you can imagine cases of other lenses where you have a source that it's very early in the universe, at an epoch in the lifetime of the universe where star formation was crucial, and we still don't know much about it. Right. Because it's too far away and things are too dim to observe back then. But with lensing, you get the boost of magnification. Now, this type of study, as well as substructure, small dark matter halo studies, they become more dependent on your model, right, on the assumptions that you put in, biases, priors, all this kind of stuff. So in order to make bold claims now for these very exciting science applications, this is where we really want to push, right? Because this is really the benefit of lensing. So we're really aiming to push in that direction. We need to have sharper tools. Right. This is what I will put, for example, in my grant proposals to claim, look, guys, we have this fantastic data, we have these techniques, we just need to understand them more, apply them to the data, and tell something about dark matter or the early universe, however you want to see it.
So coming back, now this is just me because I'm fascinated with gravity. I mean, I used it on volcanoes, and I'm going to try to set up this question better than I did previously, especially we're now going to look further afield to like the future. We've already kind of touched on the different priors and how it all comes in, and now I'm going to ask another question about gravitational waves. I'm sorry, it's just me, my personal biases, and quite frankly, I do this podcast because I'm super interested in all forms of science, and this one hits right in the sweet spot. Okay, I'm also going to put my ignorance on full display. So here it goes. Electromagnetic.
Probably me too.
Electromagnetic radiation. In other words, light, for EM, is both a wave and a particle. It physically travels or propagates through the universe following the bending of space, going in straight lines. Gravitational waves, in some sense, maybe should be thought of like seismic waves, where disturbances of an earthquake cause energy to be propagated through a medium instead of being carried by a force particle. Is the analogy of an earthquake and the merging of black holes or a collision of neutron stars propagating through space, is that a reasonable analogy?
I would say yes. Disclaimer is that I'm not a gravitational wave expert, but I have some understanding. The answer is yes. You can think of it as a very similar thing to an earthquake, like two merging black holes, for example, when they collide. As they collide, it's as if a strike-slip fault is happening, and it's moving to the two faces of the rock are moving, sliding past each other, something like that. But the difference here is that the medium through which the energy propagates, it's dissipated, it's space-time itself. That's the key idea here. So, and it's hard a bit to grasp this because space-time is the fabric of the universe. It's really the most fundamental thing it's made of, and it happens to vibrate. And it not only through theory, through general relativity again, which set the foundations for understanding the universe in terms of this intertwined space and time, and it also predicts gravitational waves. It's also observed now. We observe these things, so we know that they exist. We know that space-time vibrates. It's really tricky to measure its vibrations, but we have done it, and we are evolving it. We are improving our instruments. They are getting more sensitive, and so on. So we open up a new window to the universe, if you like. So there is another analogy here. So when the first telescopes were created by Galileo and so on, and then the astronomers used them to look at the sky, they were looking at the optical part of the spectrum. Then we built radio telescopes. We opened a new window. It's still electromagnetic radiation, but it's a whole new window to the phenomena that take place in the universe. So you can see our galaxy, other galaxies in the radio now. They look very different. And then we open other windows, X-rays, gamma rays as well. These are all electromagnetic radiation. Now we have added gravitational waves here, which is not electromagnetic radiation. It's vibrations, waves of space-time itself. And now we have so the universe, if you look at it in gravitational waves, in a few years from now, decades, we will have an image of the universe in gravitational waves. That would be, we can produce an image of that. We will be able. We are far from it, but we will be able.
That's amazing. Okay, now to carry this analogy perhaps further than it should go, when I think about seismic waves and I think about like amplification of them, it's to do with the medium it's traveling through. So all of a sudden you hit this particular unconsolidated sediment, you can amplify the waves, but you dampen its energy. So it's medium dependent of what it's traveling through. Is there any way, because it's a vibration of space, that there's any changes either perhaps due to expansion rate or other things that could change its magnification or how it moves through the universe?
Right. So the obvious here, and it links to the lenses, of course, is
exactly.
When you have a lens. When you have a lens, something happens to these waves. You are focusing them in the same way as you focus rays of light from the source. If you have rays of gravitational waves, you can refocus them when you have a curved space-time, which is a lens, basically. So you can get this, yes. If the rest of the properties, things like dark energy, things like even cosmic strings can enter this game, if these things are there and how they affect gravitational waves, this is really the limit of my knowledge. And I think it's also the limit of how we understand things in the universe right now. We can have wild theories. We can try and couple these things. We can try and say, look, if you detect a phase shift in this type of gravitational wave, for example, this means that you have time-dependent, time-varying dark energy. I'm sure there are things like that. I just made this up right now, but I'm sure there are things like that.
If you've been on social media and science groups, there's all kinds of different ideas, we'll call them.
Right. But through my career, I shifted from loving these crazy ideas and theories that can really change our understanding of the universe. I refocused my attention to the data and what the data can tell us about the universe. The ideas are nice, but we know for a fact that 9 out of 10 theories are wrong.
Absolutely.
There is one that is correct, right? Or more correct than the others.
We should really call them hypotheses, though, shouldn't we?
Exactly. So we still need to gather more and better quality data from gravitational waves in order to be able to push further our knowledge about these things, how they travel through the universe and what we can learn about the universe from them.
Okay, stepping back into your stuff specifically, and we've already touched on dark matter. We also touched on how physicists are looking towards the cosmos to explain particles like hot and cold dark matter, and all of that stuff. And even we just discussed about gravitational lensing. So what are you looking forward to in the future? Are we looking to getting more information to perhaps rework relativity? Or, I mean, where do you think this is going to go as we step forward in even next year or 10 years from now?
This is a very nice question. So first of all, there is a tidal wave of data coming our way, and it's already here with Euclid now. It's discovering more lenses that we can handle right now. So we have to work on modeling them and understanding them. So last week I was at a conference in Boston with colleagues from the field, and we discussed exactly this type of problems and how we should try and address them now. So the conclusion was that, yeah, Euclid is fantastic. It's already giving us more than we can handle. So first thing is to improve our techniques in order to be able to handle more data. There is a counter argument here. Do we really need all this data, or just having a few gems hidden in this deluge of data that will be enough to revolutionize, the dark matter, for example, to detect warm dark matter or self-interacting dark matter? And then we focus only on these, which comes back to the talk about the discussion about the analysis tools and the gravitational imaging technique and how we detect these substructures. So we really need to to improve our methods, but not to handle big numbers, but just to be like the battleship approach, as a colleague of mine used to say. You really need to model the heck out of a couple of lenses, and then you are done. You don't need to model 10,000 lenses. 5 would be enough, for example. So we are in this crossroads, or in this bifurcation, let's say, where we need to pick and understand, not just pick randomly, and just understand what will be more fruitful in terms of science. Eventually, the ideal would be to model everything as good as we can, right? But we cannot do it right now. It's unrealistic. It will require, millions of years on supercomputers. So no, sorry, we have to find another way.
It's a good problem to have, though.
It's definitely a good problem to have, and also for the future generations, because more people are joining the field, fresh minds, new ideas. Maybe in 5 years from now, we will have solved these problems and we will be ready to have lensing as a mainstream tool now. It's still a bit of a niche because of the techniques that are involved in the inverse imaging, the de-lensing techniques, all this stuff, make it a bit esoteric. As soon as we resolve these problems, us, the lensers, the modelers, then it becomes a mainstream field for many other people, many other colleagues.
Perfect. I'm so excited. I love it. Yeah. But now it's time. This is the most important question on Whimsical Wavelengths, the one I ask every guest, and it just might become the standard for the field. What is your favorite science joke?
That's a very good question. I think it's the one with the physicist, the mathematician, the computer scientist, that they all stay in the same hotel, and there is a fire in the middle of the night. So the physicist takes the extinguisher, puts out the fire, then the fire starts again. The other colleagues do their thing as well. And then the mathematician wakes up, sees the fire extinguisher, and then they say, oh, there is a solution, and they go back to sleep.
Okay.
I don't know if it was up to your standard. But
hey, it doesn't matter. They're all up to my standard. It doesn't matter how terrible they are. In fact, the more terrible, the better. I mean, you've now listened to the first part of this, and I have some terrible science jokes and puns. The more, the merrier. Okay.
I can say I said it in a rush way. Maybe I can say it again.
It's okay.
If it doesn't
We all
work out.
know your battery is about to die, but thank you so much for being here on Whimsical Wavelengths. And if you publish another paper, you want to get into it, call me up. We're glad to have you back on.
Thank you so much, Jeff. We can surely be in touch for the future. If you want to discuss your geophysical models and stuff like that, I would also be happy. This fascinates me as well. Thanks again for the invitation. It was a pleasure to have this podcast with you.
So that was awesome. And went a lot longer than I expected, as things usually do, especially on a topic so wide-ranging as gravitational lensing writ large. But you know what? If you like this episode, if you like Whimsical Wavelengths, hit subscribe. Please, please, please leave a rating. That's like the number one way people find new podcasts. Or tell a friend. Either way, I'll see you back here in 2 weeks.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us it's always. Colors intertwine, painting